Welcome back. So we're now in the process of creating image patches and turning them into patch embeddings. And we figured out that we can use a Conv2D layer to take an image. Well, this is a patchified image, but we have an unpatchified image, and we can use a Conv2D layer to turn it into patches of size 16 by 16 by setting the kernel size of our Conv2D layer to 16 by 16. So we get this square here. And then it goes to the stride, so it steps over to this next patch and does that for every single one. And then it's going to turn each of these into a convolutional feature map of embedding size. We've set it here, out channels, D size from table 1. So now we've got this tensor after we pass a single image through our Conv2D layer. Now I might just explain what's going on in this size so we can just have a little bit more of an understanding. Now we've passed a single image to our Conv2D layer. Its shape is, and so I might just turn this into some code. And you might have already jumped ahead to the next stage, and if you have, as in flattening these outer dimensions into a single dimension. And if you have, well done. Otherwise, that's what we're going to work towards in this video. So we want to flatten these two outer dimensions into a single sequence because that's going to be the input to our vision transformer. So if we go up here, this is what we've done. We've done this part so far. We've turned each of these patches into an embedding, but we want to flatten these embeddings into a sequence like this. So let's just define what's going on here. We have, this is the first dimension on the batch size. I might just actually put this as a comment so it's a different text. And then we have embedding, dim, and then we have feature map height and feature map width. These are all learnable, by the way, because I believe if we go image out of conv, let's have a look at what it looks like. Beautiful. So it's turned our image into a whole big list of numbers, but you see how here it's got grad function. So that means the gradients, I wonder if I call requires grad on here. The gradients of this tensor will be tracked by PyTorch, and they will be updated behind the scenes by gradient descent when we pass it through our training loop, and the optimizer gets called optimizer.step. These values will update, forming a better representation, hopefully, of our image over time. And that will account for every image in our data set. So to make this a little bit more concrete, how about we view some of the feature maps? Because this is what we're working towards. We want to combine these feature map height and feature map width into a single sequence. A sequence like this, because that's what the transformer is built to work with. A sequence of vectors. So this is the block that we're working towards, hybrid architecture. We've done the first step, formed a CNN feature map. Now we want to, here, the input sequence is obtained simply by flattening the spatial dimensions of the feature map. Well, what is this feature map? It's these 14 by 14 on the end. So let's visualize. Let's go plot random convolutional feature maps. Now, embeddings, I'm calling feature maps, embeddings, similar word. So import random. Let's go random. We'll select random indexes of random.sample along our embedding size. So because we're using an embedding size of 7, I might actually do just leave room for 10 at the end. Oh, excuse me. Range 0 to 758, and then k equals 5. So because we've got 768 14 by 14 feature maps, we want to randomly select 5 of these. So we're not visualizing every single one, otherwise there would be too many. So I might just put an E in here. I'm not sure how indexes is spelled. You might correct my spelling there. So print, let's go showing random convolutional feature maps from indexes, and then we'll go random indexes. Wonderful, let's just see if this works. So yeah, we've got 5 random indexes. So now we want to use these random indexes to index on this dimension and visualize these 2 dimensions. So a fair bit going on here, but you know the motto, if in doubt, code it out. Let's go fig axes equal plt.subplots, and I'm going to go n rows equals 1 and ncols equals 5 for 5 columns, 5 random samples. I mean, subplots has been our friend in this section so far, hasn't it? Let's go plot random image feature maps. So we want for I and IDX, which is short for index. In enumerate, we will go random indexes, which is that list of random indexes we just created there. We'll come down here. We'll go image conv feature map equals image out of conv. So our image passed through the conv layer up here. A single image, we passed it to our conv2D layer, which is set up here, conv2D. In channels equals 3 for color images. Out channels equals 768, which is for the D size for table 1 for vit base. We're focusing on vit base to begin with. Kernel size equals patch size. Stride equals patch size. So we'll just come back down here. Now we want to index on here, get everything from the first dimension, because the first dimension is the batch dimension. But here's where we want to go IDX. So because this is going to loop through these IDXs, we only want to select IDX on the embedding dimension. So we don't want to get all of them, we just want to get 5 random ones. And then we want to get everything on the feature map height and everything on the feature map width. Wonderful. So let's go here. Index on the output tensor of the conv2D layer. And now we can plot it. So axes i.imshow, we want to show the image conv feature map that we just created in the line above. And we're going to have to squeeze it to remove the batch dimension. And we're also going to have to detach it and turn it into numpy so that it plays nice with matplotlib. So I'll just write here, remove batch dimension, that's what squeeze does. Remove batch dimension and remove from grad tracking / switch to numpy for matplotlib. Now you can try it without those things and you'll probably get an error. In fact, why don't we try that? Command X, let's see if this works. I might eat my words here. Axis I, and then I'm going to set the X tick labels just for some aesthetics here. It's important to make good looking plots, you know? Y tick labels equals empty list, X ticks empty list, and Y ticks equals empty list. You guessed it. Okay, you ready? Let's see how this looks. We might get an error here. Oh my goodness, we've got 5 plots. There we go. Can't call numpy on tensor that requires grad. There we go. So this is where that error was coming in. Use tensor.detach.numpy, and you'll often find this if you're trying to plot tensors that have gradients tracked. So we checked out this before by going image out of conv.requires grad. This is how we know that our feature maps are learnable or our embeddings are learnable, because PyTorch is behind the scenes going to track their gradients. So I just put back in these detach and numpy, which was the suggestion here, tensor.detach.numpy. So thank you for the error codes, PyTorch. Let's run that and see what it looks like. Okay, so these look like nothingness, but behind the scenes, they are actually what our convolutional feature map looks like. So if we were to closely look at this image, we would sort of be able to make it out in these feature maps. So if we ran it again, have a look at 5 more feature maps. Now this is not the best image to visualize, so I might just run all again so we get a new image. And while that's running, let's prepare some code. So what do we want to do? So we want to get a single feature map in tensor form. Single feature map. This is just another part of visualization. Image out of conv. We haven't got to the flattening of the later dimensions yet. So this is just going to be a single feature map. And let's go single feature map. Hopefully we get a better looking image. Oh, okay. So that's got some outlines above. We're looking good here, people. .requires grad. So this is what our single feature map looks like. A whole bunch of numbers, and it requires grad. So this is going to be a learnable representation of our image. So what does our image look like now? Pizza. So there's a pretty definite sort of line there. I didn't really have the words to describe that, but an outline of a pizza. Now, if we look in this feature map, can we kind of see? You can kind of see where those outlines are. So if we run this again and have a look at 5 more random, we get some outlines here. And you might want to try this with your own images. Of course, your image may be different to mine, but if I keep running this, we get slight different. Now, of course, these are going to change over time, and we don't necessarily need to understand what's going on with these ourselves, because this is what the computer is going to recognize our images are as. So these are just random convolutional feature maps to begin with, but these will be learned over time. That's the important point. So let's keep going. What are we trying to do? We're trying to flatten this feature map into a sequence. So we want to bring this row over here. Maybe we use the last one because it's got more space. So this is the first row. Then we want to bring this row up here. So we've got over to there. Then this row up here. So we've got over to there. And so on and so on. So that the input sequence is obtained by simply flattening the spatial dimensions of the feature map. So this is the feature map, and we want to flatten the height and the width so it's a single sequence. And we can do that with the flatten layer. So let's go here. We want 4.4, flattening the patch embedding with torch nn.flatten. And now, to prevent this video from getting too long, I'm going to issue a challenge. I know we said we were going to take care of this in this video, but I thought it was important to visualize what a feature map actually is. This is a learnable representation of our image created by our Conv2D layer. So right now we have an image of this shape, or an output from our conv layer, which is 768 feature maps of size 14 by 14. But we want to change these two last dimensions, we want to flatten that into a single dimension of 196. So my challenge to you is see how you can do that with the flatten layer. Can you take this input, pass it to the flatten layer, and get an output that is in the shape of 1768196? That's what we're after. So give that a go, and I'll see you in the next video.